Good morning, everyone. I think I should be live now, so you should be able to see and hear me, hopefully. Yeah, I hope you're all doing well and are ready for some updates. Very exciting updates. I'm a little bit nervous for this one, to be honest, because this is showing off some stuff that I have been working on for quite some time, and I have not shown it at all on YouTube yet, mostly because I'm not really sure how to explain it, because it's a little bit hard to explain, but hopefully it will make sense. This is sort of, I'm using this as sort of a dry run for, at some point in the future, I want to make a proper video for all of this stuff to make it really easy to understand with like nice animations and everything. So I'm using this as a dry run to sort of get a feel for how to explain this sort of thing. And hello, Darkman and Dine. I don't know. Anyway, let's get on with it. So today we are looking at Jugglebot's brain. And just before we start, actually, I want to do a little bit of housekeeping from the last video, where there were a few people who asked, why don't I have a dedicated motor on the hand? So maybe I can actually show, nah, that's a bit risky. Yeah, so the Stewart platform moves the top part around, and then the hand is going to throw the ball. And there's been a few people who ask, why don't I have a motor just straight on the hand strings so that that motor can just like yeet the ball whenever the timing is right. So that means that there will be 6 motors for the platform to move around and a 7th motor for the hand. And if you're familiar with kinematics and this sort of thing, you might realize the problem with this, which is that that will be an overdetermined system. So the ball, the platform, or the hand rather, the hand that's actually throwing the ball can only ever move in 6 degrees of freedom. It can translate in the 3 ways and it can rotate in the 3 ways. But by adding a 7th motor to control this 6-degree freedom system, this is called being overdetermined. And when you have an overdetermined system, you have to just set rules about how the different things can behave. And I tried this for a little while. This was a while back, and it got really messy really quickly. To give an example, this is an outline. After I got a little bit confused with how all of my functions and everything were relating to each other, this is the map that I drew out to sort of figure out how everything fit into each other. And it got very confusing very quickly. Granted, I was trying to do a lot more with this code than I'm currently trying to do. I was trying to introduce a lot of juggling site swap theory, which we'll get to down the road. There's information about that on Zulip as well, if you're curious. And yeah, I was just trying to do too much at once, and the overdeterminedness of that system did not help at all. I do agree that having a hand motor, like a dedicated 7th hand motor, would be great. It would really be able to launch the ball super, super high. But I'm not familiar enough with how to deal with overdetermined robots to do that right now. So I think the better option is to stick with a fully determined system. So 6 motors, 6 degrees of freedom. And yeah, just figure this out first. And then maybe later on, if someone shows me how to do it, or if I learn how to do it, then add in the overdetermined motor, because that would be nice, but it's very confusing. It's hard to know what that 7th motor should be doing in the different situations. Yeah, it's kind of like you just have to pick, which is a bit annoying. And Kalman filters are very useful. I'm actually using them, well, I will be using them later on with the eyes, which maybe I can talk about at the end of this. But I don't know how they would be useful for the overdetermined stuff. Yeah. If you have any ideas for specifically applying it to overdetermined robots, definitely let me know. Yeah, that's an interesting idea. So the overview of the whole controller now with a fully determined robot, 6 motors, 6 degrees of freedom, is that we have a planner or controller. I'm not really sure what I want to call this just yet, but this piece of code will be sort of monitoring everything and making sure that everything's happening at the right time. It's sort of like the captain of the ship controlling everything. That will communicate with a class called path creator, which will create the path segments. So these will be like the the empty hand segment when it's not holding the ball and it's going from where it just threw to where it's about to catch, as well as the holding path where it has just caught and now it's moving to the position where it's throwing. So those are the two path segments, and that path creator code will create both of those segments. And we covered a lot of that in last week's video, but I'll touch up on it a little bit again this week. This planner and choreographer also, once it has that path, it will communicate with a hand class, which does all of the inverse kinematics, which I'll explain in a sec, for the hand. And then that goes into the Stewart platform, inverse kinematics. And then that goes into can handler, which is, can is like the communications that I'm using. And then the can handler class just deals with all that communication. So that's sort of the general flow of how this code works. And we have classes are in blue, and I've only just recently learned about this thing called a functional program where you have functions instead of classes. And I think that a functional program can be very useful for this planner choreographer thing because it doesn't actually need to store any information. It's just kind of processing it. So if you, as we're going through this, if you're familiar with functional programs, let me know if you think that this can be useful, because I've only learned about them 2 days ago and it's all kind of new to me how to apply this. Yeah, so the path creator class is the first one. This is creating the paths. And this is how we get these nice paths that I showed last week, where the ball, the hand is perfectly meeting the ball and it's all nice and smooth. And we covered all the position stuff last week and getting all the velocities right and everything. The only thing that I want to add about the position for now is that we're adding a timestamp as well. So the way that those points are getting spaced out is over time. So it'll be like, you should be at this point at this time and then this point at this time. And those points are spaced so that if, it's going to be confusing to say that. They're basically spaced around so that the velocity is smooth the whole time around. And we're adding those timestamps in so that we'll have basically like one row of our list of numbers will be like the position, the rotation, which we'll get to in a sec, and then the timestamp. So we've got position and the time, but how do we know what the rotation of the platform should be? This might seem fairly straightforward, but I have found it to be not straightforward. And I've gone through a couple different approaches with this so far. One is to base the rotation of the platform off of the Bezier control points. So you might remember from last week that these curves that are constructed here are made by Bezier curves, and these have control points that look a little bit like this. So for the red one, there's control points like this. And then, nope. All right. That's not going to work. And then for the green one, there's other control points that are like down here. And my idea was to use these control points to set sort of like an intersection point, this point I, and make it so that the platform is always perpendicular to that point. So there's always a line that can be drawn from where the platform currently is to that intersection point, and then that line is always perpendicular. And this actually works really well and is fairly not too hard to compute, but this has problems if these two lines, like if the catch position, the catch velocity and the throw, I guess I'll go the other way. If these two lines never intersect each other, if they're like skew lines, then that intersection point doesn't even exist. And so we can't use that intersection point as a sort of rotation and as a point of rotation. And that will potentially happen in some cases. And I want to make a system that is robust enough to be used in 3 dimensions. And I expect that that will probably happen at something like that is physically possible for those lines to be skew. And so I want my controller to be able to handle those sorts of cases. So this worked in 2D, but not in 3D. Another idea, which someone actually suggested in the comments of last week's video, is to track the ball so that the hand is sort of like always pointing towards the ball. And that also works really nicely, particularly when there's only one hand and one ball. But once you add in more balls and more hands, it's kind of less clear which ball you should be pointing towards. And I can imagine situations where the ball that is being pointed towards very quickly changes and the hand will be experiencing a very quick angle change. it's possible that this would be workable and would actually like do a good job if adding in like an acceleration of that angle was a thing. That might work, but that's not what I'm currently doing. What I'm currently doing is to transition from the throw angle to the catch angle so that it will basically see what angle we're going to be throwing at and see what angle we're going to be catching at, and then just linearly interpolate between those two and just slowly move between them. This is probably the same thing as tracking the ball, to be honest. It might actually work out to be exactly the same, but this is how I've sort of imagined it. And this seems to be working quite well. And this would be robust to skew lines and all that sort of weird business. Yeah, so I'm happy with that one. Yee. And at the very end of the path creator, so once it has figured out all these positions and figured out all these rotations, it makes a big old list with all of the hand states for that path, where a state is the position, the orientation, and then the time that it should be at that position and orientation. And it makes this big old list and then spits it out. And something that is worth mentioning about this path creator class is that these paths have to be created as a whole thing. I can't just create part of this path because of how the Bezier works and because of how all that like velocity scaling from last week, that requires that the entire path is computed at the same time. So I can't just do like half of it at once. I have to do the entire thing for either the empty path or the hold path. And so I can't do like half. And that comes up a little bit later. This is also not on GitHub yet, so you unfortunately cannot see this code yet. But hopefully in the next week, I will put it up. So before we go much further, actually, I just want to answer David's question about the pointing at the ball will be catching. I think that the throw angle, catch angle thing will effectively be doing that. But yeah, I'm not too sure. So I think that there are cases where if you're pointing, like if you're aiming to be pointing at the ball that you're catching, the ball that you're catching can actually change during, like over the course of the catch. So if the hand is empty and it is expecting to be catching, say, like a ball here, it's possible that before it catches that ball, another ball will come in and now that's the one that's going to be catched. And yeah, I think that this angle thing will end up being the same, but there are cases where you have to very quickly change which ball is being caught. And I think if we aim to point at the ball that's being caught, there's going to be some like discontinuities there, potentially. Yeah. So before we continue further, it's worth just having a little brief explanation of what is inverse kinematics. If you haven't heard this term before, it's a fairly useful one for robotics. So forward kinematics is if we are told that the actuators are all given positions, like for the Jugglebot's example, if we're told all of the actuators are these 6 lengths, like actuator 1 is 100 millimeters, actuator 2 is 150, blah, blah, blah. If we're told all of those lengths, where is the end effector? And the end effector is just a fancy robot word for the thing that you care about. So in my case, it'd be like the center of the platform. Like where is the center of the platform given how long all the legs are? As it happens, for Stewart platforms, that's actually super hard to do and leads to some mathematically uncertain cases that are really annoying to deal with. But thankfully, I don't need to deal with them because I'm dealing with inverse kinematics, which is the opposite of this. So what we do is if we know where we want the end effector to be, so if we know where we want the center to be with its position and rotation, which is what constructs pose, then where are the actuators? So if we want the center to be here, rotated this way, how long do all the legs need to be to make that true? And as it turns out, that's actually super easy to do with Stewart platforms. But we'll get to that in just a sec. So following the flow from before, we had path creator. This is creating the path for the whole pattern. And then once we have that path, we're sending that path to the hand class, because that path is telling us where the hand needs to be. It's not telling us where the platform needs to be, it's telling us where the hand needs to be so that it can catch and throw the ball in a smooth manner. So we know where the hand is and what angle it's at. But we don't know where the platform is, and that's what this class does. This goes from the hand pose to the platform pose. The way that this works is we draw some vectors. So we know this H vector, we know exactly where that is. We want to find this P vector. And with vector math, I personally really like the fact that you can draw this out and do it graphically. And once you have drawn it out, you can just connect up all the arrows, and then if the arrows start at the same point and they end at the same point, then those two paths are equal to each other. So all we need to do here is get an arrow that joins P to H, which is this one. S stands for displacement, and the subscript here is this is the displacement of the hand relative to the platform. Yes, so if we add P plus SHRLP, then we'll get equal to H, because those lines, those vectors start at the same point down here, and they both end up here. So these paths, H and PSP, or PSHP, these are equal to each other. Now, just a very minor technical point for anyone who's wondering, SHRLP is a scalar value, and E0 is the unit vector in the direction of the orientation of the hand. So E0 is E orientation, and that will go out here somewhere. I couldn't figure out a good way to denote this because of what is about to be in the next couple lines, but that's how that works on a bit more technical level. Now, so we have this equation. We want to find what P is, but we also know that the position of the hand relative to the platform is equal to the length of this P vector minus the length of what that P vector was at the beginning. And this is because of the way that the hand is set up. As the platform moves around, as the distance between the base and the base of the platform increases, that will pull the hand up. And if you're unsure of why that's the case, have a look at my last video, the last live stream, and maybe the one before as well. And that describes how the hand and the whole platform sort of works. But that's sort of that's mechanically how that is set up. And I want to add an asterisk here. Well, Pi is the initial P vector, like what it is and in the base state. I want to add an asterisk here because this is only true with the current hand multiplier of 2. If I increase this hand multiplier, as I suggested I would in the last video, then this would be like 2 times that length, or 3 times that length, or some fraction, or whatever. But right now, the movement, the displacement of the hand relative to the platform, so this length here, is equal to how long this P vector has increased compared to what it was at the beginning. Yes, and this ends up making the math a little bit annoying because we end up with this equation here, and we need to solve for P. Now, I'm no mathematician, but I could not figure out a way to do this analytically, where that means like I can't figure out an equation to solve this where I can just plug in the numbers and I'll get P out easy peasy. I can't figure out a way to do that because of the way that this like vecnorm thing works. Yeah, so what I've done instead is, let me get rid of my scribbles. I've been applying a Newton-Raphson method to numerically solve for this. And if you're curious, all the code is here. I will be uploading this onto GitHub soon. I need to kind of tidy things up and move things over so that I can actually use it more properly with my actual robot instead of a simulation. But this is how I've implemented it so far. And it's very messy. It's really kind of tedious and yeah, messy, but it works. And that's nice. Something that I just want to point out here as well is that I haven't implemented numeric solutions too often. And something that I'm noticing with this, when I was kind of troubleshooting this, when I was actually writing it, I noticed that this numeric solution very rarely takes more than one iteration to solve for. So what I'm doing for the numeric solution is I'm just guessing that the hand is where, I might be misremembering it, but I'm basically making a very crude guess for where the hand is and then applying one like case of this equation, and then it pretty much always gets the answer within a tolerance of 1 micrometer. And I find that very strange that it's always doing it in like 1 or 2 iterations. I've set it to be able to predict 100 iterations, but it's always doing it within 1 or 2. that makes me feel like it should be able to be solved analytically, because like the numeric solution is like pretty much bang on there every single time, but I can't figure out how to do it. If you are very good at math and you know how to solve this analytically, please let me know, because that will make my code a lot simpler and would be nice. So that's how the hand inverse kinematics works. And the objective there, just to clarify again, we are going from the known hand position, which we figured out with the path creator, and we're figuring out where the platform needs to be to put the hand in that spot. Once we know where the platform needs to be, then we can use the Stewart platform class. And this is the more relevant inverse kinematics for anyone else, really. Stewart platforms are used for a bunch of things, and this inverse kinematics I've seen explained in very weird, convoluted ways, and I've seen a lot of people online refer to this inverse kinematics as being notoriously difficult and all that sort of stuff, but it's actually really simple if you visualize it the right way. And I did not visualize it the right way for a long time, but once I did, it's so much easier. So this class handles all the inverse kinematics for the Stewart platform. And to see how this works, we can have a look at the platform. And note that I only have like a flat basic platform here, because at this point, we've already done all the hand inverse kinematics, and we know where this platform is in space. We know its position and its rotation. And now our objective is to figure out how long all of these legs are to put the platform in that spot. So the way this works, we can have a look at one leg first. L is what we're trying to solve for. If we can find L, then we are happy. And to find L, again, the way that vector math works, if we can find a path that starts from here and ends here, then that path is equal to L. It doesn't matter if that path goes like all over wacky directions. If it starts and ends in the same spot, then those two equations are equal to each other. So the task now is to figure out what other vectors can we use here that we know that can fill in the gaps, so to speak, and make these two paths. One of the vectors that we know for sure is this OB. For anyone wondering, O is reflective of this being in the base frame. That's like a superscript before the B. It's a bit of a weird notation, but this doesn't really matter. You can just ignore this if you don't know what it is. B is like the base length. So the distance, the vector from the center of the base to this specific leg node at the base. Similarly, we also know the position of the platform node with respect to the center of the platform. These two, OB and PA, like P is the platform frame, OB and PA, these are geometrically known. I can just go into SolidWorks and measure and like figure out what these values are. These are known, these are always constant, and they're never ever changing, because these parts are very rigid and they never move relative to each other. And we can see we've almost got a full loop here. The only thing we're missing is this vector, T. And T is the translation of the platform, the center of the platform, with respect to the center of the base. It doesn't technically need to be the center, but it's a lot easier if it is. So if we know this T, and we do because we know where the platform is supposed to be, we can complete this loop where we've got PA is known at the beginning. This is known as soon as the platform is built. OB, same thing. T, we're finding because we know what position we want the platform to be, and so we can construct this loop. There is one minor little niggle that makes this beautiful, nice graphic a little bit annoying, or a little bit simplistic, is this R. And I don't want to go into too much detail here on how R works, but it's basically a way of including, is how you include the rotation of the platform in. So T is the position of the platform, and R is the rotation of the platform. I plan to make a full video on how this works at some point in the future, and I will go into a bit more detail then. But I can't figure out a way to show R in this nice diagram here. It kind of ruins the truthfulness of it, which is a bit annoying, but whatever. So we've got this equation that relates all of our vectors to each other, and we want to find L. So all we need to do is rearrange, and we'll just have L is equal to T plus R PA minus OB. And we can see this is my code for this, and this is exactly what we've got. We've got the vector for the legs is equal to the position plus R times A minus B. And this is what I would love to have for the hand. If someone can find an analytic solution to the hand equation that I showed before, This is what all of that nasty code would reduce down to. And it would be beautiful and nice. But I could not find it. And if you're curious and you want to check this out in more detail, this is on GitHub in the core Stewart platform code. Cool. So at this point, we have the list of all the positions where the hand needs to be, and we are able to take those positions and orientations and turn them into Stewart platform positions and orientations. And then with this Stewart platform class, we can take those positions and orientations and turn them into leg lengths. So if we wanted to, I'll talk about this a bit more at the end, but if we wanted to, we could construct big lists of where all of the legs are for both paths and just store those lists and be done with it. And then we could just basically move through those lists. And that's where the planner / controller, if you've got a good name for this, let me know. That's where this comes in. So this code will track the current time, hopefully as accurately as possible. It will also store these path segments, so the ones created by path creator. These path segments are the hold path and the empty path. And then based on the current time, it will get the next coordinates from those path segments. And if needed, it will interpolate between two neighboring points to figure out where it should be at this exact instant. Can we call it Michael? I feel like that might get a bit confusing. Once we have the hand pose for this current spot, we figure out the hand and the platform inverse kinematics, and then we command the robot to move using the can handler. And once we have completed a given path, we will repopulate the next path so that we have at least one path segment ahead of where we currently are. So yeah, the general idea here is we have these two big lists. Every time we complete, say, the empty path, we will immediately run another piece of code, the path creator one, that will pop in the next empty path below the hold path that is just about to begin. So that way we're always at least one path segment ahead. And then at the given time we're at, figure out where on this big list of points we should be, given the timestamps of those points, and then do all the inverse kinematics to figure out, to like tell the robot to move to that point. This does involve a lot of code being run very quickly. So all of that inverse kinematics would have to be run as fast as possible. And that is a potential downside to this outline that I've given here. And that's why I have, as this is also not on GitHub yet, unfortunately, but hopefully next week it will be. This is why I have some questions, but I'll get to them in just a sec, actually. So one final recap of how this is all working. We have the planner. This is choreographing everything. This is running iteratively. I'm planning on it not being a class because functional programming seems like a good way to go. This communicates with path creator to create the path segments. Once it has those path segments, it will figure out where it needs to be at this given point, figure out the hand inverse kinematics, figure out the Stewart platform inverse kinematics, and then tell the robot what to do. And you'll notice here that this is a very straight, it's a linear path, right? Like all of the information is coming from the planner. Some of it is coming back from the path creator, but the actual control side is just unidirectional. It's just sending information out to the robot, and it's never actually getting any feedback to tell if it's doing everything right or wrong. And this is where the eyes will come in. So the eyes, the plan is to have them update the catch position and velocity based on where the ball actually is. So if the eyes detect that the ball is not where we think it is and is in fact somewhere slightly off, then we will have to update the catch position, create a new path segment for that path, and then send the new commands out to the robot. And this raises some questions for me to you, because I am not 100% sure how to do some of these. Well, I'm not 100% sure what the best way to do some of these things is. One is how should I efficiently update the path segments on the go? So right now, this path creator thing, I haven't actually timed how long it takes, but it seems to be fairly quick. But if I am updating the positions of the balls like 100 times per second, for example, with the camera seeing the balls that quickly, this means that I'll be needing to run that path creator code very, very often, Right now, it only needs to be run when the path is complete, so it can be as inefficient as I like. But once the eyes are installed, this is going to have to be computed often, like super often. So I'm not too sure what the best way to do that is. Something that's been kind of lurking in the back of my mind throughout all of this is the idea of threading. And I am not very experienced in programming, in case you haven't figured that out already. And I've seen threading done and I've used it a little bit for some things, but I'm not that familiar with when it's that useful and what the implications are of having multiple threads, especially if these threads are communicating with each other often. I've been talking with ChatGPT about this a little bit, and it seems like threading is good if the two systems are very isolated from each other, but if they need to communicate a lot, which a lot of my code does, it seems like it makes this a bit trickier. But the general idea here is that I would have a thread for the can handler, and that's just doing all the communications. So that has its own dedicated resource stream to handle all of its communications. Another one for the inverse kinematics, so that way that code, like that way calculating the inverse kinematics doesn't affect or slow down the other stuff happening. And potentially, instead of storing just the path, I could store the final result of all the leg lengths, like I mentioned before. So that way, the process of going from, okay, the time is like 1.2 seconds, that means all the leg lengths need to be exactly this long. That seems a lot faster than going, okay, the time is 1.2 seconds, so the hand needs to be here, so let's do the hand inverse kinematics, and then do the platform inverse kinematics, and then the legs need to be here. Feels a lot more efficient to do all of the leg calculations first, and have that just as one big list, but if I'm updating the position of the catch all the time, then I'll need to be running all that code all the time. And it's just messy. So I don't know. Yes, this will require a shitload more CPU, especially when I am updating the positions on the fly. So I'm not too sure how that should work or could work. And yes, the final question is the utility of functional programming. And my understanding of functional programming right now is that you, rather than having a class that kind of has its own instance of the class and it can store information about that. And so, for example, I have a class for the Stewart platform, and that retains all of the information of the geometry of the Stewart platform. That's all neatly packaged in that class, and I don't need it for any of the other classes, so it just stays there. It figures out what it needs to figure out, the leg lengths, and then spits that information out to the rest of my code, and it's a nice, neat little contained thing. But for something like the planner, I don't need it to retain any information. It's just processing information. So I feel like functional programming can work well in that case to just update the current state rather than having to store anything. But if you have any thoughts about this, please let me know, because yes, it's been about 36 hours since I learned about functional programming and very new to me. Cool. So that's it for this week. It's, yeah, a little bit heavy on the math and the physics of everything, but that is how robots work. So yeah, hopefully that made sense. If you have any thoughts about how I can explain this better, please let me know, because I plan to make like a whole video series on the control of Jugglebot with like really nice animations and everything. And yeah, I appreciate any feedback, because any feedback you give me now will go straight into making the actual video for this better, which would be good, because there's not that, like, when I was learning how to control Stewart platforms, there's just so much conflicting information out there. People use different terminology, different notation, and it was just super confusing. But as soon as I realized this whole vector thing, it's just like, oh, it's just 6 letters or 7 letters or whatever it is, and you just add them up and then done. And if you get the if you get the code to do it, you just have to figure it out once and then you're done. Like, yeah. Just looking through the comments. Yes, David, I could do that. I could test the code in a loop and see how fast it can go, but I just haven't yet. There's so many different avenues in this project that I can and should really go down, but for one reason or another, I've taken the path that I've taken, which often means that I miss some things that I could or should do, such as that. But yeah, I just haven't done that yet. But you're right, it is a good idea. And I think for me so far, I think the reason why I haven't done that sort of thing yet is because I haven't actually implemented any of this in the robot yet, and so I don't know if there even are significant bottlenecks. Like if the robot runs totally fine, then it doesn't really matter how fast the code runs because it's fast enough. But if the robot starts to be stuttery or anything like that, then yes, I will absolutely be timing like every single little thing to see where it's getting slowed down. Features with the O drives for feedback. Yes, there are features with the O drives, sort of with the O drives. So I've got rotational encoders on each of the motors, and CanHandler has a method for getting the positions of the encoders, and that's quite good. And yeah, O drive does like a bit of like estimation of where the motor actually is, because apparently it's tricky to do that in real time. But yes, that does work, and that's been very useful for like comparing the commanded position that I've been giving the platform to the actual position that it's actually moving in. And yes, that is very useful. But if I think you're mentioning that in the context of figuring out where the ball is being thrown from, like if at the instant that the ball is being thrown, I poll all of the legs to figure out where they all are, then we can figure out where the platform actually is using forward kinematics, which is nasty for Stewart platforms, but it could be done. Then we can figure out with a lot more accuracy where the ball is actually being thrown to. That will work, well, should work, and should provide another useful piece of information about where the ball is being thrown from. However, I don't like the fact that uses forward kinematics, because that is not good for Stewart platforms. And I also have, hopefully, a more robust way of doing that that doesn't involve the forward kinematics. And that's to use an inertial measurement unit, an IMU, which I plan to stick to the bottom of the hand, or the bottom of the platform, so that as the platform moves around, the IMU will figure out exactly the position of that platform. And so I can do the same sort of thing. As soon as the ball is thrown, I can poll for that position. I can poll for that orientation. I don't exactly know how I would do position with that, and maybe we would have to do the forward kinematics with the leg lengths to do the position, but I can at least get orientation, and that should be super accurate because the IMU that I've got seems to be very, very good. And I think that would be a lot less computationally involved than the forward kinematics for the Stewart platform. Maybe. We'll see. Yeah. Okay. All right. I will not worry too much about threading then. Thank you, David. And yeah, I'll focus on just getting it working. And then, yeah, I guess same thing. If things are running slowly, or if I'm having some issues, then yes, threading will be considered. That's, yeah, good idea. Thank you. Yeah, so that's about it. Hopefully that made sense. And yeah, I will see you next week. I hope you all have a lovely weekend. And yeah, till then, have a good one.